All right, let's get started taking a look at how to use the digital multimeter we'll be doing in week 11. Again, it's a review of the same circuits we developed in the online modeling software, and we'll take a look at, in particular, how to use the multimeter to take voltage, current, and resistance measurements. A couple of key ideas. So this model for a resistor, where the voltage is measured across the resistor and the current passing through the resistor is determined, is the basis for Ohm's law, where the voltage is the current times the resistance. So these are the key ideas. The voltage and current are taken while the circuit is operating, and then the resistance, it's best measured when the resistor is removed from the circuits. All right, so let's take a look at what we've got going on here. This is our digital multimeter. It's a typical Harbor Freight type piece of equipment, but it does have some good elements here, particularly working with people unfamiliar with electrical concepts. Has fused outputs, which allows us to make errors without damaging the equipment or breaking fuses that would typically be in a meter, less expensive meter. So let's take a look at this. This will power up the this will be plugged into your computer, and the microcontroller will be plugged in and providing power. As mentioned in the previous work, here the 3.3 volts are provided here and ground, and they're transferred over to the breadboard. Again, you should watch the video on how the breadboard works. That'll make some of this more clear. Just for a second here, I'm going to take out this piece that powers up the series resistance circuit, and let's take a quick look at our LED lighted circuit. So as you can see, if I press the button here, we're closing that circuit. I'm going to switch back to our other piece here. So here's that, again, that close-up of that breadboard power LED. Again, 3.3 volts comes in and attaches and is plugged into the red side of this part of the breadboard, and the ground is plugged into the blue side, this part of the breadboard. You can see that the LED is plugged into the 3.3 volts and then jumps into one of the columns on the breadboard, which goes into the switch. And so referring to the image on the right, so the 3.3 side of the power supply gets plugged into the LED, and the LED other leg goes into the switch. And this switch is shown yellow here because it's closed. So then from the switch, it travels into another column here through the resistor and back to ground, or the negative side of it. So out of the switch, through the resistor, and back to the other side of the battery. So when the switch is closed, as it's shown in this part of the drawing, we get the lamp illuminates. So let's switch back to our picture and demonstrate that one more time. So we'll push this, and as you can see, the lamp lights up. Now let's take some just quick voltage measurements on this circuit. These won't be recorded, but I do want you to take a look at it. So the voltage measurement is shown here. It will automatically choose if it's an AC or a DC signal. For us, DC is the default, and we have the proper settings are here in the volts, ohms, and hertz setting for the red, and then the common is the black side. So when you've got them plugged in correctly, it will, or incorrectly, it warns you, and correctly it gives you a bit of advice there. So when it's set up to measure voltage and you touch the probes together, it essentially goes to 0. So let's take a look at the LED here. I'm going to touch the red one to the positive. I'm just going to stick it down in the hole with the LED wire, and then stick it down in the hole with the other side, and then press the on button. So here you can see the voltage across that LED is 1.69 or 696. Okay, and you know this is providing 3.3. Let's do the same thing on the other side. I'm going to put the positive here on the same side of the resistor. Let's take the voltage across the resistor, and then press the button down as well. And here the voltage is 1.519 or 1.52. Okay, so again, that's how we're going to measure voltage. When measuring voltage, say on the power supply, for example, we can touch the wire that's in the red part of this breadboard and touch another wire that's sticking into the blue part of the breadboard. And here we can see instead of 3.3 volts, the power supply is actually generating 3.258. Very close. That level of accuracy for a microcontroller like this is very typical. And so I'll move my hands out of the way a little bit. So again, I'm touching a wire that's that's sticking into the red side and touching a wire that's sticking into the blue side. Let's zoom that in just a little bit. Take one more look at that. Again, touching the red side and the blue side, and then the measurements, excuse me. Oops. The measurement 3.258. Okay. All right, so that's the breadboard lamp. So if you're not sure if the power is getting over there, this is the quick way to check. And we could force it to do that all the time. All right, so now let's take a quick look at the other circuit. We'll switch back to our, so that's this circuit closed, this 3 resistor series circuit. And again, this shows the LED off and test points. So we've tried to replicate as best as possible in the real world here with our measurements that are going to be taken here. So we need to, I removed the 3.3 volts wire plugged into the red side, and then I'll restore it to the beginning of the series of resistors. So our first experiment was to do this with just one resistor. So I'm going to pull out the 2 intervening ones here. And in our first experiment, we connected like this, so that the voltage is coming out of the power supply through the first resistor, out of the power supply through the first resistor and then back to the negative side. So in terms of measuring voltage, we're still set up correctly, and you can measure the voltage by touching across the resistors. So one on the right, one on the left. I'm just pressing it down into the hole with it. All right, and again, our voltage is 3.139. Now that is negative because I did swap the terminals, and it's important to understand this a little bit, but if I move this back and put the ground here, it's positive again. So it's a voltage drop, so we've got 3.3 volts coming in and then 3.3 volts also dropping across that resistor. So here's the difference in terms of measuring the current. So what we'll do with the current this time is we have to break the circuit as we mentioned. I'm going to switch it to current, and you'll see that we have to make a change. And, excuse me, the common stays and the red one moves. So now the current is going to pass through between these two and go through the meter and measure the current in the system. So again, these resistors, we'll double check the resistance here in just a second, but in order to break the circuit, I'm going to just scoot over this wire here and make a connection with it underneath, and then make the same connection that it was plugged into. So again, we're taking from the 3.3 into that resistor, and we're reading 3.19 milliamps with this one. Okay, so we'll restore that, and now it's still working. The voltage is passing through it. So let's do one other thing. I'm going to pull this resistor out and break the circuit. And so measuring the resistance is the last piece of this. So I'll switch to resistance. It warns me to set it up to read correctly, and I'll touch one side of the resistor and touch the other side of the resistor and hold it and let it stabilize. In this case, it's 9.978 kiloohms or 979 ohms. And of course that matches very closely with what's in your videos that you watched already. So I'm going to restore this circuit and set up the second circuit and restore the connection between the two from the first resistor to the second resistor. And our first measurement would be voltage again. So we'll switch back, and it's still correct. It's not warning us that we've got the wrong one. And we'll come in and measure the input voltage one more time. .258, and then the voltage across the resistor. And it's okay if the numbers are backwards. You just have to remove the sign. So voltage across this one, voltage across that one. How come our circuit's not closed? Oops, I missed one here. Close the circuit there. Okay. So 1.59, that varies a little bit, moves around, and then we'll measure the other one. Try not to touch more than one wire. And 1.610, I have to check the other one. 1.59, so they're within a few hundredths of each other in terms of voltage. So again, you'll be recording those voltages. And now we want to check the current, so we'll switch down to milliamps again. Since it's such a small current, switch over so that we can measure that. And this time we'll measure the current going between the resistors. And we need only connect from the first one, since the wire we just removed. We'll connect there and touch the next one. So the current in this situation is 1.61 milliamps. Now, just to confirm it's the same everywhere, we want you to take measurements on the before as well. So I'm going to open this circuit one more time, make contact here, and close this, 1.62. And then finally restore that, break the circuit on this side, make connection here underneath that, and with the last wire. Again, oops, did I miss a connection here? Oh, there we go. All right, and again, it's reading negative 1.6. That the only thing that's happening there is I accidentally crossed up my wires, so it was going through backwards through the meter. So again, 1.62, the same current throughout everything. So that's how you're going to take measurements. So the last thing you'll need to do is set up the last circuit, which is the 3 resistor series, and complete the last set of measurements for that one. So we'll set you up for the parallel circuit. It's a bit different, and complete the same measurements in studio.